Hi, in this video we're going to discuss how the second derivative can be used to find and classify critical points. So here on the left-hand side we have a local minimum. Notice at a local minimum we always have that the function's concave up, and so often the second derivative will be positive. On the other hand, if you have a local maximum, then we have something that's concave down, and so the second derivative is negative. So we're going to use these ideas to formulate what's called the second derivative test. So the second derivative test is a way of finding critical points and classifying them. Well, as before, the first derivative test, we have to first find the critical points by using the fact that either the derivative is zero or does not exist. That's how you find the critical points. And then to determine whether they're local maxima or local minima, you can use the sign of the second derivative. In particular, if the second derivative is positive, then we're concave up, and so we have a local minimum. If the second derivative is negative, then we're concave down and have a local maximum. Now, something strange happens when it's equal to zero. If second derivative is equal to zero, you can't say anything at all. We don't know anything. In that case, we have to revert back to the first derivative test. Okay, let's look at some examples. Find and classify the critical points of f of x equals x times e to the x. Okay, so in order to do that, I first want to find the critical points. So I want to find the derivative, f prime of x. Well, by the product rule, that will equal 1 times e to the x plus x times e to the x. Now, this always exists. I can always plug in x and nothing funny will happen. But so I only need to check where f prime of x is equal to 0. Well, f prime of x is equal to 0 if and only if 1 times e to the x plus x times e to the x is equal to 0. So I want to solve this for x. Okay, so one thing you can do here is you can factor out the e to the x. You can write 1 plus x times e to the x. So I factored out the e to the x from both terms, and I want that to be 0. The only way this can be 0 is if either 1 plus x is 0 or e to the x is 0. But e to the x is always positive, no matter what x is, and therefore the only way that this product can be 0 is if 1 plus x is 0. In particular, you can divide both sides by e to the x, and I get 1 plus x is equal to 0. And that happens only if x is equal to minus 1. So this is my only critical point. Okay, now I want to determine, is that a local max, a local min, or maybe neither? So to do that, I'm going to take the second derivative and check for concavity. So second derivative is obtained by taking the derivative of the first derivative. So the derivative of e to the x is simply e to the x. The derivative of x times e to the x, well, I just did that. I have e to the x plus x times e to the x. And I can simplify this a little by writing 2 times e to the x. I have 2 of them, plus x times e to the x. And now I need to take my critical point, which was x equals minus 1, and plug that in to the second derivative. So f double prime of minus 1 is 2 times e to the minus 1 plus minus 1 times e to the minus 1. Okay, so that's the same as 2 minus 1 times e to the 1. That is, I have 2 e to the minus 1s here, minus 1 e to the minus 1s here, so I'm left with only 1 e to the minus 1. But e to the minus 1 is positive because e to the x is always positive, so this is a positive. What does that mean? That means that I have concave up, which means the picture looks like that is, and so I have x equals minus 1 is a local min. Let's do one more example. Find and classify the critical points of g of t equals t to the fourth. Okay, again, I find the critical points. I find the derivative first. G prime of t is equal to 4 times t cubed, 4t cubed. And now I find out where where is that 0? Where doesn't it exist? Well, it always exists. I can plug t in for any t, and I get out an output. So I want to check where is that equal to 0? Well, it's only 0 when t is equal to 0. So that's my critical point. And then to check, I check whether it's a local max or min, or maybe neither, I can try the second derivative test. So that requires I take the second derivative, which again by the power rule is going to be 12t squared. And now I want to evaluate that at my critical point, which is t equals 0. So I take the 0, plug it in for t, 12 times 0 squared, and that's equal to 0. But that doesn't tell me anything, because remember, in the second derivative test, if the second derivative is 0, can't say anything. So let's move. So what can we have to do? In this case, we'll have to apply the first derivative test. Okay, well, the first derivative I've already computed. Now I have to check to the left and to the right of 0 to see what happens. Well, if you check a negative number, if you take t equals to a negative number, you'll find that this is negative, and so to the left we'll have a negative for the derivative. And when x is bigger than 0, this will be positive, so we'll have a positive number. What does this mean? It means that the function is first decreasing. Derivative negative means decreasing, and derivative positive means it's increasing. So what we have is that this is a minimum. So t equals 0 is a local minimum by the first derivative test.